Welcome to Selection with Sathi. Today we will master hashing and hash tables with code on screen. Hash tables provide average O of one time for search, insert, and delete. We will cover hash functions, chaining, probing, load factor, and more. This is heavily tested in GATE CSE and coding interviews. Let us begin. Let us start with the hash function using the division method. Look at line 3. We compute the index as key mod m, where m is the table size. Line 4 stores the key at that computed index. A good hash function distributes keys uniformly across all slots. The table size m should be a prime number, far from powers of 2. This minimizes clustering and gives better distribution. Computing the hash takes constant O of one time. What happens when two keys hash to the same index? That is a collision. Chaining is the simplest solution. Look at line 2, we compute the index, then line 3 appends the key to that bucket's list. For search, lines 6 through 9 show, compute the index, then scan the chain. Insert is O of 1 since we just append. Search takes O of 1 plus alpha on average, where alpha is the load factor n over m. Worst case, all keys collide and search becomes O of n. Now let us look at linear probing, a form of open addressing. Line 3, compute the initial index. Line 5 is the key part, while the slot is occupied, increment I. We check slot index, index plus 1, index plus 2, and so on. Line 7 places the key once we find an empty slot. The problem with linear probing is primary clustering. Long runs of occupied slots form, making future inserts slower. Load factor must stay below 1 for open addressing. Quadratic probing reduces clustering. Look at line 5, instead of adding I linearly, we add I squared. So we check index, index plus 1, index plus 4, index plus 9, and so on. This spreads probes more evenly, but may not visit all slots. Double hashing is even better. Lines 9 to 11 show the idea. Use a second hash function h2 of k for the step size. The slot is h1 of k plus I times h2 of k mod m. Double hashing gives the best distribution among open addressing methods. The load factor alpha equals n divided by m. When alpha gets too high, performance degrades. Line 1, the rehash function creates a new, larger table. Line 2, new size is roughly double, but we pick the next prime. Lines 4 through 8, we reinsert every existing key into the new table. For open addressing, rehash when alpha exceeds 0.7. For chaining, alpha can exceed 1 but chains get long. Rehashing costs O of n but happens rarely, so amortized insert stays O of 1. When should you choose a hash table versus ABST? Lines 1 through 5 show hash table operations, search, insert, delete all O of 1 average, but no ordered traversal. Lines 7 through 11 show BST, all operations O of log n, but you get in-order traversal for free. If you need fast lookups without ordering, use a hash table. If you need sorted data or range queries, use ABST. Hash worst case is O of n with bad hash, BST guarantees O log n if balanced.
Let us trace insertion with chaining. Insert 15, 22, 37, 29, 8 into a table of size 7. Line to 15 mod 7 equals 1. Slot 1 chain becomes 15. 22 mod 7 equals 1. Collision. Chain at slot 1 becomes 15, 22. 37 mod 7 equals 2. Slot 2 gets 37, no collision. 29 mod 7 equals 1 again. Chain grows to 15, 22, 29. 8 mod 7 equals 1. 4 collisions at slot 1. Chain is 15, 22, 29, 8. Load factor is 5/7, approximately 0.71. Now linear probing. Insert 10, 22, 31, 4, 15 into table of size 7. Line 310 mod 7 is 3. Slot 3 empty, place directly. 22 mod 7 is 1. Slot 1 empty, done. 31 mod 7 is 3. Slot 3 taken by 10. Line 5, while loop probes. I becomes 1, check slot 4, it is empty. Place 31 at slot 4. 4 mod 7 is 4. Slot 4 now taken by 31. Probe to slot 5, place there. 15 mod 7 is 1. Slot 1 taken. Probe to slot 2, it is empty. Final table, empty, 22, 15, 10, 31, 4, empty. How fast is search in a hash table? Table size 10, 5 keys stored, so alpha equals 0.5. Look at the search code, lines 2 and 3 compute the index and scan. For chaining, successful search averages 1 plus alpha over 2, which is 1.25. For linear probing, the formula gives about 2 comparisons. For double hashing, it is 1 over alpha times the log of 1 over 1 minus alpha, about 1.39. All methods give roughly 1 to 2 comparisons. This is essentially constant time lookup. Deletion in open addressing requires special handling. We cannot simply empty the slot because probing chains would break. Look at line 1, we define a Tombstone sentinel value. Lines 6 through 8, scan for the key using the same probe sequence. When found, line 8 marks the slot as Tombstone instead of none. Future searches continue probing through tombstones. Future inserts can reuse Tombstone slots. This maintains correctness of the probe chain.
Quick exam tips. First, table size should be prime and far from powers of 2. Second, chaining is simpler but open addressing has better cache performance. Third, rehash when load factor exceeds 0.7 for open addressing. Fourth, in gate, count collisions and probe sequence length carefully. For more DSA concept videos with code on screen, download the Selection with Sathi app. Like and subscribe. Thank you.